and continue with our thematically linked talks this morning. And it's my pleasure to introduce Shasha Zoe this morning, who's going to give a plenary tutorial, continuing with the magnetosphere, ionosphere, thermosphere coupling theme. Shasha did her PhD at UCLA with Larry Lyons, and has since moved on to the University of Michigan, where she's become much more agnostic about her opinions on the magnetosphere. And we're going to, I think her talk is going to reflect that today. All right, Shasha?
Okay, thank you very much. First, I would like to thank the CEDAR and the GEM steering committee for inviting me to give this plenary tutorial. Okay, so I'm going to talk about the dynamic high-latitude ionospheric convection, its drivers and effects. I will talk about the solar wind and the IMF as the external drivers for determining the basic convection structures. I will also talk about the modification of the convection patterns due to internal magnetospheric processes. In terms of the effects, I will cover 4 aspects. The first one is more global, the neutral dynamics effects. And the other 3 are more regional, but I organized them from the day side to the night side, so bear with me. The solar wind and the magnetic field, the interplanetary magnetic field embedded with it, interacted with the Earth's intrinsic magnetic field. It changes the shape of the magnetosphere. The day side is compressed, the night side is elongated. There are 2 major processes for the momentum and the energy from the solar wind to transfer into the magnetosphere. The first one, and the most important one you already heard about this morning, is a reconnection. So here is the new midnight meridional plane of the magnetosphere. When the IMF has a southward condition, component, it will reconnect with the Earth's northward magnetic field on the day side, generate 2 new open field lines, the red lines here, and then the solar wind will drag those open field lines from the day side to the night side, where they will reconnect again. The newly formed closed field line will drift backwards towards the Earth and go around, trying to finish the loop. At the same time, in the ionosphere, the footprint of the magnetic field will also move from the day side through the polar cap, anti-sunward, and then sunward at a lower latitude, form those concentric circles, where we call them the convection pattern. For southward IMF condition, the situation is easier. It's usually 2-cell convection pattern, dusk cell, dawn cell. The noon is right here. The red line here is the open-closed field line boundary. Polarward of this open-closed field line boundary. The fields are open with one end in the ionosphere and another end loose in the solar wind. Equatorward of this boundary, the magnetic field are closed with 2 ends connecting the northern and the southern hemispheres. Now the pink shaded area is the plasma sheet, where the energetic particles precipitate into the upper atmosphere, generate ionizations, cause aurora. So the plasma sheet, and the aurora oval, which probably you can see now very clearly here, are magnetically connected. The aurora oval is like a 2-dimensional imaging, tell us a lot of the process that's happening actually in the plasma sheet. Another process for the energy and the momentum to get into the magnetosphere is through the viscous interaction in the equatorial plane. The closed magnetic field line drift anti-sunward in the low latitude boundary layer and comes back in the plasma sheet, form those closed loops again. So if we map those viscous convection cell into the high latitude, they are those green circles here, closer to the open closed field line boundary on the 2 flank side. During northward IMF conditions, the reconnection can also happen, but in this case, we call it a high latitude reconnection because it happens even tailward of the cusp region here. You can have reconnection happen in both hemispheres or just one hemisphere. The high latitude reconnection related convection cells closer to the pole, and in the opposite direction as the reconnection-driven convection cell during southward IMF condition. But the viscous convection cell at lower latitude is in the same rotation sense. So from a single particle point of view, in the ionosphere F region, the plasma collision frequency with the neutrals is much lower than the gyro frequency. So both the ions and the electrons will drift in the E cross B direction. That also means the trajectories of the F region plasma will also follow those circles. In the lower E region, because of frequent ion-neutral collisions, the ions will deviate from the E cross B drift. It will have a large component actually parallel to the electric field, right here. But the electrons are basically not affected. This different drifts between the positive and negatively charged particles enable the current, horizontal currents to flow in the E region. Based on the IMF clock angle, that is the angle between the IMF BY and the BD component, the empirical convection patterns have been produced. In this case, what I'm showing is based on the measurements from the Dynamic Explorer 2 data, but those convection patterns can also be derived from measurements from F region plasma drift, as I mentioned, using ground-based radars. So consistent with those simple theoretical pictures, when the IMF is southward, we have those large two-cell convection pattern. You see they extend to very low latitude, 50 degrees. For southward IMF, the convection pattern is much more complicated, 3 cells, 4 cells, very often. What's more interesting is when you have an IMF BY component, the cusp, in the dayside cusp region, actually the flow direction directly reflects the BY direction. When it has a positive component, it has the flow will drift towards the dawn. When it has a negative component, it will drift towards the dusk sector. So the cusp flow is very sensitive to the IMF BY direction. Now, in the equatorial plane of the magnetosphere, the simplest electric field configuration is the sum of the convection electric field, that's from the dawn to the dusk, and the co-rotation electric field pointing earthward. The total convection electric field, or the equipotentials, are shown here. This line is called the separatrix. Outside the separatrix, the trajectories are open. So cold plasmas following those trajectories were actually lost into the dayside magnetopause. Inside the separatrix, those plasmas were drifting in circles. And this is also the easiest explanation for the formation of the plasma sphere and plasma pause. For more energetic particles in the plasma sheet, besides the E cross B drift, they are also subject to magnetic gradient and curvature drift. The ions will drift westward, the electrons will drift eastward. The electron plasma sheet will penetrate closer to the Earth on the dawn sector, and the ion plasma sheet will penetrate deeper on the other side. Those magnetic drift are very important for the dynamics happening in the inner magnetosphere and for the shielding process. Okay, so the top plot here is an unperturbed condition under equilibrium condition. The yellow region shaded are the plasma sheet. When we impose a convection electric field, the inner edge of the plasma sheet will move earthward. At the same time, the gradient and the curvature drift will accumulate positive charged particles on this side, negative charged particles on the other side. So the electric field established by this charge separation is called the shielding electric field. It's pointing from dusk to dawn in the opposite direction as the convection electric field. So in the inner magnetosphere region, the total electric field, which depends on the sum of those two, can be reduced. The convection electric field is very sensitive to the IMF direction, as I have already mentioned. If the IMF turns northward or just less southward, the perturbation electric field can be reduced immediately. But this shielding electric field established due to the more energetic particles can stay there. So temporarily, in the inner magnetosphere region, the electric field can change its direction from dawn dusk to dawn, and we call this overshooting electric field. You can also think about this from the current closure point of view. The ions in the plasma sheet are more energetic than the electrons, usually 6 or 7 times more energetic. So the gradient and the curvature drift faster than the electrons carry more cross-tail current, partial ring current with them. In most of the cases, actually the partial ring current, the yellow shaded region here, has a peak in the pre-midnight sector. So this partial ring current will close itself through a downward region 2 field line current in the dusk sector and upward field line current in the dawn sector or post-midnight sector. So here the red means downward and the greenish means upward. So you can see a very interesting convection feature called Hurron reversal forms here. That's a skewing of this convection pattern, deviate from the two-cell convection pattern that you would imagine just based on the solar wind and the IMF driven. And this overlap between the up and the downward region 2 field line currents are suggested to be important for the formation of this phenomenon. At the same time, this downward region 2 field line current maps to a low conductance region in the ionosphere. Here, I think in this simulation, we only consider electron precipitation. So the electric field needs to increase in order to close the current. And so the equipotentials becomes much closer to each other. And this is, if you think about the particles, those are the SAPS flows, the subaurora polarization streams. So the convection feature, including Hurron reversal and the SAPS, are part of this shielding process. Okay, so I have talked about the solar wind, IMF, as the external drivers of the basic pattern of convection and also modification of the convection pattern due to internal shielding process. Next, I'm going to talk about the effects. The first effect is more global scale. It's a neutral dynamics. Okay, the high latitude ionosphere, once it starts to move, is a significant source of momentum and energy for the thermosphere because of the ion and neutral collisions. This interaction can modify the thermospheric wind pattern at high latitude, can modify its temperature and composition through frictional heating. If there is a velocity difference between the ions and the neutrals, okay, that will tend to heat actually both the ions and the neutrals. But the time scales for the ions and the neutrals to change are different. The time scale for the ions to change is very fast, only a few seconds or a few tenths of seconds. But it takes much longer for the neutrals to change because of large neutral densities, several order of magnitude higher neutral densities there in the ionosphere. In the high latitude ionosphere, the plasma density actually can easily change 2 or 3 order of magnitude in small spatial and temporal scales. That means the characteristic time constant of the thermospheric wind can change from several days to tens of minutes. Okay. We talk about the IMF and the solar wind can establish this two-cell convection pattern during southward IMF condition. And that can also drive the high latitude thermospheric wind roughly move in the same direction. You can see anti-sunward thermospheric wind here, and then return flows at lower latitude. It's not exactly the same as the ion convection pattern due to the neutral inertia and the Earth's rotation, but it does mimic what's going on in the ionosphere convection here. For northward IMF convection, condition, the convection pattern is more complicated, but the neutrals can still mimic what's going on in the convection pattern. So this thermospheric wind, mainly due to the ion drag, is imposed into the thermospheric wind pattern that you would imagine only due to the solar heating. Once the neutrals start to move, it's very hard to stop them. This is an experiment done by Richmond and Rope many years ago. This is a convection pattern that imposed, by increased cross-polar cap potential drop. And shortly after, you start to see a similar two-cell convection pattern, but in the wind. Okay. And then they turned off the external drivers. The ionosphere convection pattern, which is moving in the E cross B direction, showed change directly, almost immediately, but the neutrals will keep pushing the ions moving in the same direction. So this is the convection pattern that's due to the wind, and this is called the neutral flywheel effects. The high latitude wind, on average, play a minor role in the magnetosphere, ionosphere-thermosphere couplings, but they can play more important role when you have large activities for a long time and your external drivers suddenly turned off. Next, for more regional effects, I'm going to talk about uplifting and downshifting in the F-region ionosphere. So in most of the time, for us in the GEM communities, we think about the magnetic field as purely vertical in the high latitude region, but that's not always the case. The high latitude convection pattern can extend to as low as 50 degrees geomagnetic latitude. And as you're moving away from the polar region to the lower latitude, the magnetic field inclination angle decreases. So that actually means the E cross B convection pattern can have component in both the horizontal and the vertical direction. As an example, here in the co-rotation reference frame, this is should be the two-cell convection pattern superposed with co-rotation. And if we decompose them into horizontal and vertical drift, you can see, in general, on the day side, the vertical drift is positive, and on the night side, it's negative. This is a very subtle effect, simply due to the geometric consideration, but it can have very important consequences. Okay. Besides the E cross B drift, other processes can also induce vertical plasma drift. The meridianal neutral wind, for example, in this case, is moving equatorward. It also can push the plasma move up and down the magnetic field line. The vertical forces, the gravitational forces and the pressure gradient forces will also push plasmas move up and down the magnetic field. So the total vertical plasma drift speed is determined by the sum of all of those processes. Why should we care about that? Let's first look at the chemistry. Okay. So in the ionosphere F region, O+ is the dominant ion composition. The loss of the O+ is actually through a two-step process. The first one is a charge exchange, and the O+ charge exchange with molecules, and then become NO+ and O2+. And then NO+ and O2+, the dissociatively combine with electrons. Those two-step process is much faster than the direct radiative combination of the O+ with the electrons. So this means by moving your F-layer plasma up and down, either away or towards the denser neutral layers, this induced vertical plasma can affect the lifetime of the plasmas. So that can, again, affect the densities in the ionosphere. Such induced vertical drift can be very important for the density variabilities within the storm-enhanced density. And this morning you have heard a lot about storm-enhanced density and its importance. Here is one of the examples, the SEDs here and the plume extending actually across the polar cap region. If you have an incoherent scanner radar, measuring the densities underneath one of those red area, and you can see that during storm time, that's a blue curve, the F region peak height and the peak density, including the top side, increased significantly. Is that due to the vertical lifting? How are we going to find that out? Okay. So we can use incoherent scanner radar to help us. In this case, I used the poker flat emitter radars. Because of its fully electronic steering capabilities, it can almost simultaneously looking at different directions. So for this experiment, we had a beam looking in the vertical direction. we have a beam looking in the E cross B direction and another one parallel to the magnetic field. So we can measure the total vertical flow, and we can also measure the contribution from the E cross B direction and the field aligned direction. Okay? Here is your SED. The noon is down here. Okay? So this may be a little faint, but the solid line here is the contribution of the vertical flow from E cross B. The dashed line is from the field aligned component. In this case, both of them contribute to the upward vertical drift. Okay. In some cases, the feather radar is directly underneath the SED plume, so we can look at the dynamics happening there. This is another storm. After a further IMF southward turning, we see the sudden penetration electric field very clear, the sudden increase of the convection over several degree latitude, and the E cross B induced upward drift here, and you also see the density increase, in particular in the top side. But shortly after that, I think this only lasted for like 20 or 25 minutes. Shortly after that, your E cross B contribution is still positive, but the field aligned component becomes very large and downward, and you see the density decrease. And so in this case, we found that both the polar thermospheric wind and the enhanced pressure gradient force start to push plasmas to lower altitude where they recombine faster. So those examples demonstrate that the interplay between the convection electric field, which itself is affected by both external and internal sources, and also the thermospheric wind affected by the ion convection as well, determines the density variability within the SED and the SED plume. And not every plume can make it to the polar cap. Like in this case, this is from two different storms, but exactly the same UT time. You see, in this case, the plumes did cross the polar cap to the night side aurora oval, but in another case, it stops right there. Why is this important? Okay, because of the ion upflow and outflow that have been already discussed in the previous talks, those SED and SED plumes provide important seed population in the F-region ionosphere, topside ionosphere. They are waiting for extra energies coming from the magnetosphere, further energize them, and then excite them, eventually get into the magnetosphere. Using the global ionosphere-thermosphere models, we traced the plasma column backwards to study its magnetic local time origin and to study the major loss and the source processes. Here we are looking at the density changes right after the IMF southward turning and shortly after northward turning. The red here means the chemistries. So around 200 kilometers, the chemistry always play a negative role, causes the density loss. But after you turn on the IMF, turn to southward, you lift the plasmas to higher altitude, and so the density is increased, moving away from the layer, the chemistry recombination layer. And after the IMF northward turning, your E cross B convection disappeared, and then the plasmas start to diffuse backwards to the layer where they can recombine much faster. Okay. Using the Utah State, the TDIM model, the Healy et al. Clearly showed the effect of the polarward and the equatorward convection flows on plasma density. The plot on the top is an example of a pure zonal flow from 11 to 13 MLT. And within this 2 MLT, the total content in a flux tube only changed 3 Ts in unit. But if at the same time, the flux moves 5 degrees polarward, it can change 30 Ts in unit. If it moves equatorward 5 degrees, it can decrease almost 20 Ts a unit. So during this, through this simple experiment, we can see very clearly the effect of the polarward and the equatorward convection motion to the density. Using the time GCM, Liu et al. Estimated the contribution from the penetration electric field and the marine downwind to the total vertical drift. What they found is that depends on where you are looking at. In the subaurora region, the contribution from the penetration electric field is very important, but as you move to mid-latitude, to lower latitude, the thermospheric wind becomes more and more important. And of course, if you drive the system really hard, for example, in superstorm conditions in Huba and Susskind's study, the equatorial superfountain effect can start to pump the plasma into mid-latitude region where they can be transported by the convection pattern and bring them into higher latitude. So during those cases, the plasma circulation is indeed global. Okay, so it's a short summary for this part. The upward and the downward shifting of the F-layer plasma, simply due to the geometric consideration of the Earth's magnetic field, can have very important consequence on the ionospheric density. And I have shown the storm-enhanced density and the plume as an example. Quantification of those different mechanisms, formation mechanisms, and during at different locations during geomagnetic storm is still a very active research topic. Okay, so now I'm moving polarward. I'm going to talk about the structuring of the polar cap ionosphere. In the polar cap, the plasma patches are those high-density islands. Typical definition is that the peak density within the patches is at least twice higher than that of the surrounding region. Here is an example from the riser north radar. I think this is a vertical beam. So you can see those high density and tall stripes, the 1, 2, 3, 4, those are the polar cap patches that are measured by the radar as they drift across the radar. We can also observe them using the ground-based all-scan imagers. Like here is one like cigar-shaped, another one, they are drifting from the west to the east in this case. The high density within the patches will recombine with O2+, and then they can generate oxygen atoms. Some of them are energetic enough in order to emit the 630 nanometer emissions. And that's why they can also be observed in the either white light or the red line all-scan images. As we have seen, there are large density gradient associated with the patches. And so the patches are actually one of the most important space weather events that people are considering, deep in the polar cap. In terms of the formation mechanisms, the recent paper by Carlson et al. Summarized some of the proposed mechanisms, and all of them are related with the transient convection changes. Let's see, the first one, time-dependent reconnection and pulsating soft electron precipitation. It actually emphasized the ionization due to the soft electron precipitation. The second one here, sudden expansion and contracting of the convection pattern, IMFBY direction changes. Those two emphasize the sudden change in the convection direction. The last one, but not the least, is the enhanced recombination within a high-speed convection flow, creating low-density regions. So this mechanism emphasizes the low-density region in between those high-density patches. There is evidence for all of those mechanisms, but which one is responsible for the majority of the patches? I think that's still an open question. And is that dependent on the longitude? Very possible. Recently used the GPS TECs, David et al. Studies the seasonal and the UT dependence of polar cap patches. What you can see here is a winter time. So the patches tend to occur during winter. That's because the background plasma density is low, and it tends to occur between 12 and 24 UT. You can see it here very clearly. This is the time when the North America sector is on the day side. So because of the dipole tilt, the convection pattern can reach lower geographic latitude and bring in more high-density solar-produced plasma into the polar region. And this observation is remarkably similar to a model results that the group have done many years ago. Using the superdown and the red line all-sky imagers, Thomas et al. In 2015 showed a one-to-one spatial correlation between the superdown power and the all-sky imager air glow. And they calculated the convection speed based on the optical measurement and compared that with a radar measurement and found almost a one-to-one correlation. And the plasma velocity is around 600 and 700 meters per second. And so this demonstrates that we can use the patches as the tracers for the polar cap convection. And they have already been applied to study day-night convection couplings and the evolution of the mesoscale fast flow channels in the polar cap. As the patches being created on the day-side cusp region, they will be transported to the higher latitude, the region towards the night side, where they actually being called boundary blobs when they get into the aurora oval. Here is a modeling study done by Crowley et al. 20 years ago, used a steady state convection pattern. Initially, the patch is like this circle here in the polar cap. As time goes on, the plasma would drift along the equipotentials here, and then they spread into both the dusk and the dawn convection cell, becomes those extremely narrow in latitude and longitudinally extended structure. This is called boundary blob. And the plot on the left is a beautiful example measured by the Chantanica incoherence scanner radar. From lower to higher latitude, you are seeing the typical mid-latitude ionosphere, the trough, and here is your boundary blob, which still resembles that high density and tall structures, very similar to the riser observations deep in the polar cap. Okay. Because of the continuously increasing number of GPS TEC receivers, in particular at a high latitude, we start to be able to trace the life cycle of the polar cap patches by using data. Okay. You can see in this case, the patches are created here on the day side. They are transported towards the polar cap. They get into the aurora oval and eventually becomes the boundary blobs. Okay. Here is a summary for this structuring of the polar cap ionosphere case. The polar cap patches are important because of its actually have very practical importance. And we still don't know what is the major formation mechanism for those patches and how the convection changes would change the patch dynamics and its illumination, and how do those patches can exit the night side polar cap. Is that telling us there is a night side reconnection going on? Okay. That would be a very interesting topic to follow. Okay. So the last effect that I'm going to talk about is the ion-neutral couplings within the subaurora polarization streams and the subaurora ion drifts. SAPS has been mentioned before in the Field's talk. So equator of the aurora oval in the dusk and the pre-midnight sectors, you see the convection speed is still enhanced. The wider region is called the SAPS, and the smaller, latitudinally more narrower, but maybe the velocity peak is higher, we usually call them the SAD, the subaurora ion drifts. The formation mechanisms of the SAPS and the SAD, there are also several formation mechanisms. The one that proposed by Southwood and Wolf suggests that, and we also mentioned this earlier, this is the electron aurora zone, generated by the precipitation of electrons coming from the plasma sheet. In order to close the region 2 downward field line current, in the low conductance region, the electric fields need to increase in order to close. In this scenario, the ionosphere plays a pure passive role. It accepts whatever particle precipitations coming from the plasma sheet. There are also other mechanisms which emphasize the positive feedback between the ionosphere and the magnetosphere. The Banks and Yasukawa back in the 70s also suggested that in the collisional layers, the ions can be transported in the direction of the electric field as well. So in the SAPS channel, where in a lot of the cases, you have polarward electric field that can move the ions to a higher latitude away from the region where your electric field actually peaked. Another mechanism suggested by Bob Zhang is that once your electric field is very large, and the frictional heating will further heat the ions, and the charge exchange reaction rate is very sensitive to the ion temperature. Once you increase the ion temperature, the O+ will be converted to NO+ very quickly. I have another slide just to showing the effects due to the large electric field. Okay. If the electric field is 0, this is what the typical ion temperature profile would look like from lower to higher latitude. And at the bottom part, the ion temperature is determined by the neutral temperature because of frequent collisions. But at a higher altitude, the ion temperature starts to increase. That's because of the Coulomb collisions between the ions and the electrons are more important. So you actually see this positive gradient here. But once you have a very large electric field, in this case 100 millivolts per meter, that's 2,000 kilometer drift, then the ion temperature in the bottom part increased significantly here, about 4,000 to 5,000 Kelvin, and the gradient actually is reversed now because your heating source is at a lower altitude. The plot here shows for different electric field imposed, the NO+, O+, and the total electron density, how they evolve. Once the electric field is larger than 100 millivolts per meter, the O+ will be very quickly converted to NO+, and the subsequent recombination will reduce the electron density very quickly. Here is a beautiful example from the Dynamic Explorer 2 data. This is the electron energy spectrum. So the plasma sheet precipitations, and here is the inner magnetosphere region. The red curve here is the horizontal ion drift. In this case, it reached 4,000 meters per second. So the electric field is 200 millivolts per meter. The third panel is the ion temperature. No, it's 10,000 Kelvin, and here is the total density of the electrons. Red means O+, and the blue means the molecular ions. So in this case, you can see it's exactly the same as what predicted by the Shank simulation, is frictional heating quickly convert O+ into molecular ions, and then the densities would decrease. This actually has also interesting limiting feedback. As earlier mentioned by Rod Hillis, is once you have the lower ion density here, the momentum and energy exchange between the ion and the neutrals will decrease. So it's less efficient. It's a very interesting negative feedback loop there. Okay, now I'm going to talk a little bit about the evolution of the SAPS actually during geomagnetic substorm, still one of my favorite topic. What I did here is I superposed the super-down line of site velocities on top of the SEMIS all-sky imagers. I think the sequence goes from here to here, and then this is where the substorm onset happens. If we measure the time series of the convection flows equatward of the onset arc here, this is a time series. You can see a nice band. That's the SAPS. It forms during the substorm growth phase. That makes sense, because during the substorm growth phase, you have the IMF generally turns southward, energy start to pump into the magnetosphere, and all the shielding process started to evolve. After the substorm onset, the aurora oval will expand, both polarward and azimuthally. The brightest feature in the aurora bulge is called the westward traveling surge. Here is an example. It's a very nice, clockwise like swirl. when the westward traveling surge drifted, of course, from the east into the all-sky imager, and the radars co-located there measured a sudden increase in the convection flows. So here is a SAPS. This can be simply understood as trying to close the enhanced upward field line current at a higher latitude. You can also look at the individual beams here. And associated with each of these bright features of this westward traveling surge, you can actually see very highly varying SAPS response to those fine scale structures. Okay. Using the coupled BSRS and the CEDAR-GEM model, Butulukova et al. In 2010 simulated the SAPS response during the growth phase and after subsnomy injection. Okay. During the growth phase, you see a nice partial rain current formed here, and then the SAPS forms associated with the downward field line current. This is a growth phase SAPS. This is a pressure distribution shortly after a particle injection. And you can see another layer of partial rain current located outside of the previous partial rain current here. So this can also generate a SAPS. So you can see multiple SAPS channels. Depending on the pre-existing pressure distribution in the inner magnetosphere, depending on the particle injections and how deep they can penetrate into the inner magnetosphere. In all of the previous series, none of them considered proton precipitations. But we have known that the proton precipitation can also be a very important ionization source in the dusk side and the pre-midnight sectors. Here is an example from Nielsen 2005. The black curve here is the proton energy flux. The blue one is the electron. This is very typical in the dusk side. And here is the electron densities measured by DMSP. You can see a large trough here. The bottom panel is from the S-scan incoherent scanner radar. Again, in the F region, the green curve, you can see a deep density trough. The red curve here is the electric field, and the blue one is the Peterson conductance. You don't see a dip in the Peterson conductance. That's because of the proton precipitations. So we need to be cautious about the altitude of the trough associated with SAPS. Doesn't necessarily mean that we have a low conductance region, And also the proton precipitation should be included in the SAPS modeling. Okay, so a summary for this part. The SAPS and the SED is a really unique feature reflecting the interesting feedbacks between the magnetosphere, ionosphere, and the thermosphere. I think, observationally, if we want to tackle which mechanism is important for the SAPS generation, we will need to measure the latitudinal profile of conductivity within the SAPS. The latitudinal profile of the region 2 field line currents and the convection are relatively easier because of the availability of large scale, like ampere or super down measurements, but the conductivity is difficult. In terms of modeling, I think in order to successfully model the formation and the evolution of the SAPS, we will need to use two-way coupled magnetosphere, ionosphere, thermosphere model. We will need to calculate self-consistent conductance, including both electrons and protons. We need to do the particle injections right. Again, this depends on the pre-existing pressure distribution in the inner magnetosphere, and also the particle injections coming from the tail region. And the third one here is the chemical reactions is dependent on the plasma temperature. I emphasized the importance of the ion temperature, but the electron temperature is also very important. In the second step of the two-step loss process, the dissociative recombination is inversely proportional to the electron temperature. So the higher the temperature, the less likely that the recombination will happen. So, but the heat, the electron temperature highly depends on the heat flux you put in your simulation, and the heat flux is very difficult. Okay, so I think I've made incremental summaries, after each section. So I'll stop here and put the outline here, and I'll accept the questions. Thank you.